In this video, I am going to continue our discussion on the effect of symmetries on scattering matrix elements. We have already seen the effect of continuous Poincare symmetries as well as internal symmetries in previous lectures. In today's version, we are going to talk about discrete symmetries. In particular, today I am going to talk about the parity symmetry operation. Let me remind you that in the parity operation, the spatial components of a 4-vector changes sign, whereas the temporal component stays the same. In terms of spacetime coordinates, x0 stays x0, whereas x1, x2, x3 changes sign. So the parity operation is given by the matrix that you can see on your screen, which is a diagonal matrix, a very simple one, with +1 for the 0, 0 element and -1s for the 1, 1, 2, 2 and 3, 3 elements. Let me take this opportunity to remind you that we are using the standard convention of ordering here. That is, we are writing down the components in the order 0, 1, 2 and 3. This is different from the one which Weinberg uses in his book, where he puts the temporal component, which is still the 0 component, after 1, 2 and 3. So if you were to take a look at Weinberg's textbook, you will find that the same matrix is written with -1s along the first 3 diagonal elements and +1 in the last position. This is no different from what we are doing here. I am just following the more usual convention of putting the temporal or 0 index first. As can be easily figured out, the most immediate consequence of the parity operation is position vector r goes to -r, and since t stays the same, this immediately means v, the velocity, also changes sign. So does the momentum, so p goes to -p, whereas j, which in the simplest classical situation comes from calculating the cross product of r and p, have 2 factors, each of which change sign, so j itself does not. We also denote the same by saying that while r and p are true vectors, j actually is a pseudo-vector under parity. Polar vectors, real vectors, change sign, whereas pseudo-vectors or so-called axial vectors do not. Now, as we have already discussed in an earlier lecture, the unitary operator corresponding to this operation curly p, something which we are going to write as capital P, exists only in situations where parity is a good quantum number, or equivalent is the operation of parity or spatial reversal is a good symmetry of the system. In such cases, we have already seen what happens to one particle states under the action of the parity operator. We have seen that the massive case and the massless cases are slightly different. In the case of a massive particle, which is characterized basically by its momentum, 4 momentum p, and spin component sigma, which is really the third component of its angular momentum, the action of capital P is very simple. When capital P acts on psi p sigma, the resulting state now has 4 momentum given by curly p acting on p, which means of course p0 stays the same and the spatial part or the p vector part changes sign, and the other characterizing thing is sigma, which stays the same. Remember, j does not change under parity, so j should stay j, so its third component of course does not change. What happens is that you end up with an overall factor, a phase factor called eta. The m equal to 0 case, as I have said already, is slightly different. There, a state is characterized by its 4 momentum and sigma, but here sigma is basically the helicity, which changes sign when you apply parity. So psi p sigma acted upon by capital P gives rise to a state which is psi curly p, that is a parity reversed or spatially reversed 4 momentum, along with a helicity which has changed sign. So you have psi curly pp, comma minus sigma. The overall phase factor here bears a slightly more complicated form. It has a factor eta sigma, which depends only on the helicity state sigma. But on top of that, there's an extra factor e to the minus plus I pi sigma, where the phase is minus pi sigma or plus pi sigma, depending on whether the second component of the spatial momentum, p vector, is positive or negative. Now this was discussed in some detail in a previous lecture, and ultimately this is a consequence of the conventions that we have adopted in choosing a rotation that will create our state psi p sigma from a standard reference state. I will not prolong this discussion any further because, as far as I know, no really important physical principle actually depends on this. And in what follows, we are going to assume that all our particles are massive particles, so that the equations that we write down look slightly simpler. The massless case can also be taken into account with a bit of care, but frankly that's not going to tell us something very enriching as far as the physics is concerned, so we are not going to worry about that right now. Now this was the situation for single particle states. When we talk of interactions, and of course when we are discussing scattering matrix elements, we will talk about interactions, what we need to talk about are multi-particle states. Now, if you have a collection of free particles, as I have said, we will assume all of these to be massive just for convenience. Then, we expect there to be an operator P0, a unitary operator, which acting on the state phi, a multi-particle state with particle labels given by P1, sigma 1, N1, P2, sigma 2, N2, etc., will essentially produce a state phi with labels changed a bit. Notice that the sigma and the n label, n which is just the particle identity label, that of course does not change due to parity, neither does sigma 2 n2, but the four momenta p1, p2 gets replaced by curly p acting on p1, curly p acting on p2 and so on. That is basically the spatial parts get reversed. And just as single particle states had picked up a phase factor, the intrinsic parity factor, eta, now you have one eta for each particle species and of course labeled by the particle species numbers n1, n2 and so on. So P0 acting on phi, P1 sigma 1 n1, P2 sigma 2 n2 etc. is basically eta n1, eta n2, all of these multiplied together, multiplying the multi-particle free state phi curly p p1 comma sigma 1 comma n1 curly p p2 comma sigma 2 comma n2 and so on. Now, this would be the situation for free particles, which are of course not very interesting for us. What is much more interesting is what happens when you have interacting particles. And there, remember, we had talked about in states and out states, which essentially look like free particle states if measurements were made in the remote past or in the remote future. And the whole point of there being a symmetry under parity transformation is the following. There must exist a unitary operator capital P under which both in states and out states transform exactly like the free particle states. The important thing is the same operator capital P has to act on both the in states and the out states if the symmetry is to be a valid symmetry. And the action of capital P on the in or out states, denoted by plus or minus signs, is exactly the same as that of P0 acting on the phi, the free particle states, P acting on psi plus minus P1 sigma 1 n1, P2 sigma 2 n2, etc. is eta n1, eta n2 times psi plus minus curly p p1 sigma 1 n1, curly p p2 sigma 2 n2 and so on. Now, we have already seen this in discussions about internal symmetries, and the proof here is exactly similar. Such a P can exist only if P0, the unitary operator which implemented this parity operation on the free particle states, commutes with both the free particle Hamiltonian H0 and the interaction V. And if this happens, capital P, the unitary operator which acts on the in and the out states, must be exactly the same as P0. So, the important point here is, if parity is a symmetry, and as we will see later, it is really important to be aware that the answer to this question could be no, then you have a unitary operator capital P which acts on the in and out states in this particular manner. Just by changing the four momenta by parity reversal, not changing any other indices, and multiplication by phase factors, which are the so-called intrinsic parities for each of the particles. Now, what consequence does the existence of such a parity symmetry operator have on our old friends, the S matrix elements? Let me remind you that the S matrix element S beta alpha is nothing but the overlap between the states psi beta minus, which is of course an out state which labels beta, and the state psi alpha plus, an in state with labels alpha. So, in order to see this effect, let us take a look at the specific element with alpha and beta expanded out to write down the individual particle labels. S P1 prime sigma 1 prime N1 prime P2 prime sigma 2 prime N2 prime dot dot dot, then P1 sigma 1 N1 P2 sigma 2 N2 dot dot dot, which of course means that we are talking of a situation where the in state had particle labels given by P1 sigma 1 N1 P2 sigma 2 N2, and the out states had these prime labels. This is of course the overlap between psi minus P1 prime sigma 1 prime N1 prime P2 prime sigma 2 prime N2 prime and so on, with psi plus P1 sigma 1 N1 P2 sigma 2 N2 dot dot dot. Now, because we have assumed that the unitary operator capital P exists, we can supply both of these elements in the inner product with the same capital P as we have done here, and that is of course not going to change the overlap. That is nothing but the property of an unitary operator. But we do know what happens to these states when P acts on them. Remember, the same operator P acting on psi minus and psi plus, the out and the in states, produces the parity reversal effect. So what we have is the following. When psi minus gets acted upon by capital P, you get psi minus curly P P1 prime sigma 1 prime N1 prime, curly P P2 prime sigma 2 prime N2 prime. Once again, the sigma and the particle levels don't change, the four momenta change with curly P acted upon them, with eta N1 prime, eta N2 prime, etc., multiplying the whole thing, which is of course what you get from a product of the intrinsic parities. That of course is nothing but the first factor in the inner product. What happens to the second factor? Essentially, it's something very similar. Psi plus P1 sigma 1 N1, P2 sigma 2 N2, etc. acted upon by capital P gives you psi plus curly P P1 sigma 1 N1, curly P P2 sigma 2 N2 and so on. And once again, the whole thing gets multiplied by a bunch of intrinsic parities. All that is left now is to use a basic property of the inner product, that it is linear in the second factor and antilinear in the first factor, to arrive at our final result, which connects the S matrix elements to their parity reverse counterparts. Notice that on this side you have S matrix elements with the in-state labels and the out-state labels as they were, and on the right hand side you have the same labels but with the four momenta parity reversed. And the relationship between these two S matrix elements is simply that they are multiplied by an overall factor which corresponds to the product of the intrinsic parities of the in-state particles and the conjugate of the product of the intrinsic parities of the out-state particles. Now, let me address a question which might be bothering quite a few of you at this stage, especially when I have started talking about the conjugate of the intrinsic parities. After all, the parity operation which we carry out on space-time obviously is self-reversing. That is, if you apply it twice, you definitely get the identity matrix. And this seems to imply that the corresponding unitary operator capital P should also obey a similar relationship. Indeed, in non-relativistic quantum mechanics, when we talk about the action of the parity operator acting on a wave function which depends only on position, the result is of course psi of minus r. And this immediately will tell you that p square acting on psi of r will be p acting on psi of minus r, and that will be psi of r. And since this works for all wave functions, this will tell you that p square, the unitary operator parity squared, must be the identity operator. Now an immediate consequence of that will be that the eigenvalues of the parity operator, which are the intrinsic parities in this case, must have values of either plus 1 or minus 1. They should at least be all real, and therefore conjugation that we are doing here is not really necessary. Now the situation for full-fledged relativistic quantum mechanics is slightly more complicated. But, as it will turn out, the overall result is not very different. Let me now try to explain that in some detail. Indeed, that explanation might also explain to some of you who may be wondering as to why we are dealing with the discrete Poincare symmetries, parity and time reversal, after talking about the internal symmetries. Why did not we talk about them immediately after talking about the continuous Poincare symmetries? And the answer is that there is really a reason for doing that. Now, let us note that what the operator P does is that it acts on an in or out state and produces another state of the same kind, either an in state or an out state, in the corresponding parity reverse state. So all that happens is that among all the labels which describe the states, the spin and the particle label doesn't change, the momentum gets forward reversed. Or rather, the spatial part of the forward momentum gets reversed. But notice that if P does this, that is, changes the forward momentum by applying a parity reversal and does not affect the spin or the particle label, the same happens when you multiply P by an internal symmetry operation. That is simply given by e to the power I alpha capital B plus I beta capital L plus I gamma capital Q. Alpha, beta, gamma are real numbers here, and capital B, capital L, capital Q are nothing but the operators which implement baryon number conservation, lepton number conservation, and charge conservation. Notice that each of these operators, capital B, capital L, capital Q, act on a one particle state without changing the particle species label, but just applies an overall phase factor on this. We had discussed this in some detail in a previous lecture when we talked about abelian internal symmetries. Now what is important is the following. Since P prime and P does the same thing to the particle labels, we could just as well have used P prime as our parity operator rather than the operator capital P itself. And therefore, P and P prime are equally valid as parity operators. So the question would be, is the intrinsic parity the number eta for a single particle? Or is it the corresponding phase factor which comes about when you apply P prime on the state, that is, eta prime, which is given by eta times e to the power I alpha B plus beta L plus gamma Q, where small b, small l, small q are nothing but the eigenvalues of capital B, capital L, capital Q, or things we know more familiarly as baryon number, lepton number, and charge of the particle concerned. Now, which one is going to be considered the intrinsic parity depends on which one of the operators, capital P or capital P prime, we use to implement the parity operation. Notice that actually there is nothing to choose between the two. At a physical level, we are fully free to implement parity by using either one of them. So we will actually use the one which makes our life the simplest. What is obvious here is that eta started out as a phase vector and eta prime, this new intrinsic parity, the one corresponding to P prime, will also be a phase vector, a complex number with magnitude 1. Since we have a freedom to choose these three real numbers alpha, beta and gamma, we can actually exploit that to make eta prime as simple as possible. But frankly, we can only make it as simple as possible for up to 3 particles. If we choose for the particles proton, neutron and electron, which are the most common particles that we deal with, we notice that we have the following combinations for the conserved quantities. The neutron has a baryon number of 1, lepton number of 0 and 0 charge. Proton, on the other hand, has baryon number and charge of 1 but a lepton number of 0. The electron has lepton number of 1 and charge of minus 1. These are all different combinations of B, L and Q, and therefore what we can do is we can choose alpha, beta and gamma in such a way that the corresponding eta prime for these 3 particles all become 1. So whatever be the original etas for the neutron, proton and electron, we can choose alpha, beta and gamma in such a way for the neutron, with B equal to 1, L and Q both 0, the new P prime factor, eta n prime, will become just 1. For that we need 1 to be equal to eta n times e to the I alpha. Similarly, you can choose gamma in such a way that eta p e to the I alpha plus gamma becomes 1. And finally, we can also choose beta in such a way that eta e, the electron intrinsic parity, according to the operator capital P, multiplied by e to the I beta minus gamma also becomes 1. What this implies is that with this particular choice of alpha, beta and gamma, the parity for the neutron, proton and electron become plus 1 each, as long as you use capital P prime for the parity operator and not the operator capital P. So for these 3 particles, the intrinsic parity factors become very simple. However, notice that once we have done this, we have already frozen our choices for alpha, beta and gamma. We no longer have the freedom to redefine the parity operator after this, and as a result, we have no further choice. Let me point out that for particles like pi 0, which had B, L and Q all 0, P and P prime were identical anyway. So the intrinsic parity of particles like pi 0 cannot be redefined in this manner. You have to live with whatever you have. But at least with this choice, 3 of the simple particles that we need all the time and which react to produce many of the other particles that I will talk about, have very simple intrinsic parities, and this is the option that we are going to use. So even if our original parity operator, that whatever we chose, did the right job as far as the particle labels were concerned, but gave you non-trivial phase factors for the neutron, proton and electron, we would redefine the parity operator and ensure that these 3 particles have an intrinsic parity of plus 1. Now let us come to the question about P square, the question that we raised at the very beginning of this discussion, and is this part of the discussion, where, remember, we had already shown that P square is identities in non-relativistic quantum mechanics, leading to eta values which were only +1 or -1. Now, in a more general case that we are looking at, p square takes a state with particle labels p1 sigma 1, n1, p2 sigma 2, n2, etc. to a state with exactly the same labels. The parity operation acts on the 4 momentum twice, and that of course returns you back the original 4 momenta. The other labels, sigma and n, were not affected by the parity operation in the first place. So, p square essentially acts like an internal symmetry operation, an operation in which the 4 momentum of the helicity labels do not change. Of course, in a general internal symmetry operation, the particle labels might get mixed up, might change, or make it with a linear combination of different states with different particle labels, as happens, say, in isospin. But for abelian cases, you do not have such mix-ups. At least, you can always choose your particle labels in such a way that they don't get mixed up with each other. They don't change at all under the action of internal symmetry operations. So it transpires that p square actually is an internal symmetry operation, which is why we are studying this after we have studied the properties of internal symmetry operations. Now, given the action of p on psi, the action of p square on psi is pretty straightforward. As I said, psi p1 sigma 1, n1, p2 sigma 2, n2, etc. acted upon by p square returns psi with exactly the same labels. But what you have extra is it's multiplied by eta 1 square, eta 2 square, eta 3 square, etc. etc. Now, we have a possibility that this particular operator p square, which is a simple internal symmetry transformation, may be a part of a continuous group of transformations. For example, p square might be an element like this. It is the I alpha b plus beta L plus gamma Q. In other words, the phase factors which p square produces are exactly the same as the phase factor that this particular operator uses. Here, alpha, beta and gamma are specific choices for real numbers, which of course have nothing to do with the previous choices we have made to make the intrinsic parities for the neutron, the proton and the electron equal to 1. These are just independent alpha, beta and gamma. But if this is a continuous group of symmetries, that is, all alpha, beta and gamma allowed as far as internal symmetries are concerned, then within this group of internal symmetry transformations, you must also have this element. E to the power minus I by 2 times alpha b plus beta L plus gamma q, which essentially is effectively the same as this, but with alpha, beta and gamma replaced by minus alpha by 2, minus beta by 2 and minus gamma by 2. It's obvious what we are trying to do here. If I define my p prime by p times ip, that is, we change our parity operator to this one, this will be an equivalent parity operator to whatever we had. And what it obeys, and this one obviously obeys p prime square equals identity. After all, IP was designed in such a way that it commutes with capital P and a square cancels out p square. So, we can always redefine our operators in such a way that p prime square, the new parity operator, so we can always redefine our operator. So, in such a situation where p square belongs to a continuous group of symmetry transformations, we can always redefine the parity operator so that this new parity operator squares to 1, and then all the intrinsic parities can only take values of +1 and -1 because they have to all square to +1. At this point, I must confess that I was slightly confused between the two different redefinitions of P that Weinberg talks about and the ones I have just explained to you. After all, Weinberg claimed, and as I have explained already, that you can ensure that the intrinsic parities of three of your favorite particles, maybe neutron, proton and electron, can be set equal to +1 by redefining the parity operator by including into it a term like the I alpha b plus beta L plus gamma q, where of course alpha, beta and gamma would have to be chosen to ensure that the intrinsic parities for these three particles come out equal to 1. Now here, what we have just now talked about, the attempt to make p prime square equal to 1 requires you to multiply p by something which is also of the same form, but presumably with other values of alpha, beta and gamma. The confusion, of course, was, wouldn't these two redefinitions conflict with each other? Maybe I would be able to make p prime square equal to 1, thus ensuring that the intrinsic parities, the etas, are either +1 or -1, but that may rob me of my ability to actually make the phases, the intrinsic parities of these three particles equal to +1. Maybe they will end up with -1. However, at this point, let me point out that while I did say that either I alpha b plus beta L plus gamma q is what p square would have to be equal to if it were a member of this particular internal symmetry group, this alone does not tell you what alpha, beta and gamma are. Remember, capital B, capital L and capital Q, as far as we know, have only integer eigenvalues, and that means that alpha, beta and gamma can be redefined up to multiples of 2 pi. You would not be able to tell the difference of either I alpha b and either I alpha plus 2 pi times b. Now, because alpha can be redefined by multiples of 2 pi, alpha by 2, something which goes into the definition of IP here, is only defined up to an additional factor of pi. In particular, what you could do is choose these multiples of pi judiciously to change any -1s you had for the intrinsic parities of the three particles into +1. So there is really no conflict between these two things that we have talked about. Of course, one thing has to be clearly borne in mind. This last redefinition that we talked about, the one which makes p prime square equal to 1, can be carried out only if p square, which is an internal symmetry operation, is part of a continuous internal symmetry group. It could even be that it's part of some other internal symmetry group which has nothing to do with B, L and Q. If that were the case, then of course there will be no conflict between these two redefinitions. However, as far as we know, the elementary particles that we encounter in our daily lives essentially have baryon number, lepton number and charge as additive conserved quantities or generators of abelian symmetries, and therefore this is the situation that we actually encounter. There is another possibility which Weinberg talks about, and I am going to discuss this next. Please note that as far as experimental evidence available today is concerned, this next thing that I am going to talk about is not necessarily what we observe in our daily world, but we could, in principle, have a situation like that. This concerns the possibility that p square, which as we have just seen, is an internal symmetry operation, is not part of a continuous group of symmetry operations, but it is equal to some discrete internal symmetry operation. Then IP, the so-called inverse square root of p square, would not actually be a symmetry operation, and therefore redefining p prime as p times IP, while it will give me an operator, it will not give me a conserved operator which can work in place of the parity operator. So this redefinition, which ensures that the eigenvalues of P be plus minus 1 and also the intrinsic parities of particles be always plus minus 1, may not be possible in such a situation. Now notice that a possible such situation can arise in particle physics. At least no fundamental rule that we know rules this out. And the possibility is as follows. Since angular momentum is a conserved quantity, F, the total number of particles with half-integer spin can only change by an even number in a reaction. Of course, if the total number of fermions or total number of particles with half-integer spins were different between the initial state and the final state, the total angular momentum of the initial state would definitely be different from the total angular momentum of the final state, which is not a possibility according to angular momentum conservation. And this automatically means that minus 1 to the f, a number which is plus 1 if f, the total number of particles with half-integer spins, is even, and minus 1 if it's odd, is a conserved internal symmetry operator. And so, can't this be possible that p square turns out to be minus 1 to the f? Now, it turns out that even if this were true, that would not really change things much in the world as we know it. Because, as far as we know, for all fermions, the baryon number added to the lepton number leads to an odd number. In other words, as far as all particles are concerned, minus 1 raised to the power capital F produces exactly the same result as minus 1 to the power b plus L, which of course is e to the I pi b plus L. That is, alpha equal to pi, of course modulo multiples of 2 pi, and beta equals pi, again modulo 2 pi, would work perfectly well here. And this will fit exactly into the discussion that we have just had. So redefining p into p prime given by minus 1 to the b plus L by 2 times p gives rise to a conserved parity operator p prime whose square is the identity. So as far as known fermions are concerned, even this possibility of p square being equal to minus 1 to the f would not lead to a departure from p prime square being equal to 1 and hence intrinsic parities being plus or minus 1. However, if a conjectured new kind of particle, a Majorana Fermion, were discovered, then this whole thing will change. A Majorana Fermion is a fermion which is its own antiparticle, and as a result, all the additive conserved quantities corresponding to this particle must vanish. So it must have b equal to 0, 0 baryon number, and 0 lepton number. Now, the Majorana fermion is a spin half particle. So if you had a Majorana particle, then it's possible to have p square equal to minus 1 to the f. But here, minus 1 to the f will no longer be equal to minus 1 to the b plus L. Note that b plus L for a Majorana fermion is 0. So minus 1 to the b plus L would be plus 1, whereas minus 1 to the f, if a reaction occurred where you had an extra Majorana fermion on one side, would be minus 1. So in such a situation, it would be impossible to redefine p square and ensure that the new parity operator has eigenvalues of plus and minus 1 only. Let me point out though, that even if you had Majorana fermions, p square equals minus 1 to the f would still imply p to the 4 is minus 1 to the 2f, minus 1 raised to twice the number of fermions, and therefore you would end up with plus 1. And hence, in this case, the possible intrinsic parity values can only be plus or minus 1 or plus or minus I. The last pair, plus or minus I, would actually be intrinsic parities for the Majorana Fermions. So this is a hypothetical scenario which we would have to adopt if Majorana Fermions were discovered. However, as far as we know today, Majorana Fermions are theoretically possible but not experimentally observed among elementary particles. Therefore, we would still be able to live with a parity operator whose eigenvalues are only plus or minus 1. One more consequence of this would be that the relationship between S matrix elements, between direct reactions and parity reverse reactions, would become this, where the conjugations on eta n1 prime, eta n2 prime, etc. can be ignored because these are now real numbers, either plus 1 or minus 1. And of course, this overall factor that you have here can either be plus 1 or minus 1. So we have two possible cases. One is when the product of the intrinsic parities that you began with is equal to the product of the intrinsic parities of the particles that are produced in the distant future, and therefore this overall factor here will be plus 1. And so what you have is this result. The S matrix element will not change at all when you change all the momenta, in fact all the three momenta of the particles involved, to their negatives, leaving everything else the same. The other possible case is when the product of the intrinsic parities of the particles present in the remote past and the remote future are different. Of course, in this case they can only differ by a minus sign, and then the S matrix element will also become a minus sign under the reversal of all the three vectors. So the overall result is the S matrix element must be either even or odd overall in the three momenta, and this actually puts a huge restriction on possible reactions. Before we proceed further, let me correct myself, or rather, let me clarify a point that could have been misconveyed in what I said a while ago. Notice that parity operator acting on psi p1, p2, etc., I have just suppressed all the other labels, being equal to eta n1, eta n2, psi curly pp1, curly pp2, etc., immediately implies that p square acting on psi p1, p2, etc. gives you eta 1 square, eta 2 square, etc. times psi p1, p2, and so on. So what this says is that eta 1 square, eta 2 square, etc. are eigenvalues of p square. And this immediately tells you that eta 1, eta 2 are eigenvalues of p. However, I would like to point out that this equation itself is not an eigenvalue equation. The two psi's on the two sides are different. Unless, of course, all the particles involved were at rest. So while eta n1, eta n2, this product is actually an eigenvalue for p, this psi is not an eigenvector, and that is something you have to be careful about. It's an eigenvector only if all the particles were at rest, but that, of course, is a very rare situation. When you're talking of single particle states and parity acting on that, then of course you can talk about the particle being at rest, provided it's a massive particle, of course, and there the rest state of the particle would be an eigenstate of the parity operator corresponding to the eigenvalue eta. And of course, if p square is plus 1, then eta is either plus 1 or minus 1. So rest states of the particles would then be either parity even or parity odd. But let me point out that irrespective of whether the states are parity even or parity odd, what is important is the S matrix element is definitely going to be parity even or parity odd, depending on whether there is a change in intrinsic parity between the products and the reactants, so to speak, between the particles in the remote future and the particles present at remote past. Let me now go on and talk about a particular application of this to a physical situation, a very, very important application which had far-reaching consequences for elementary particle physics In a way, this application is a bit strange because we are trying to use parity symmetry here, but the end product of this application actually led us to discover that parity is really not a conserved quantity, at least not for all possible reactions. For the time being though, we are going to consider parity to be a symmetry operation for the kind of interactions that we are dealing with. Now a bit of history, maybe in order here. In 1951, a discovery was made. It was found that a negative pion, pi minus, can be absorbed by a deuteron in the ground state of pi minus d atom. An atom in which the proton has been replaced by deuteron and the surrounding electron has been replaced by a negative pion. So it was like a hydrogen atom but with different particles. The ground state of this particle was of course L equal to 0. And here the pion could fall into the nucleus, in this case the deuteron, and ultimately what would happen is two neutrons would come out. Now let us talk about what consequences this would have as far as parity symmetry is concerned. It turns out to be rather non-trivial to get to the final conclusion. We have to go through several steps. Let's do them one by one. The first step concerns another symmetry, which we know to be valid, angular momentum conservation. Note that initially what you have is a situation like this. The pion is a spinless particle. The deuteron, it was known from experiments, is a spin 1 particle. And this was the L equal to 0 state. So the overall angular momentum which came out of summation of all these three angular momenta must have been J equal to 1. Finally, after the reaction occurred and you ended up with two neutrons, they must also be in the J equal to 1 state. Note that in the final state we have two neutrons, two spin-half particles. So total spin of these two particles could be either 0 or 1. Now in order to get a final total angular momentum of 1, the possible values of L could be 2, 1 or 0. And let us now point out all the possibilities. These are the possibilities which are allowed. You could have L equal 2, S equals 1, giving J equals 1. L equals 1, S equals 1 will also give you, among all possible sums, a J equal to 1 term. L equal to 1, S equal to 0, L equal to 0, S equal to 1 will both give you J equal to 1. Now, among all of these possibilities, we can choose only one to be the correct one by virtue of the fact that neutrons being identical particles, in particular being fermions, the wave function must be antisymmetric under the interchange of the two particles. Now the spatial part of the wave function, which contains the orbital angular momentum as an important ingredient, has a parity of -1 to the L. Remember, if you interchange two particles, basically for the relative motion, R goes to -R. So parity is very relevant here. Now L equal to 2 corresponds to an even wave function as far as the interchange of the two particles in space is concerned. On the other hand, as far as the spin is concerned, S equal to 1 is a spin symmetric state. So this particular combination, L equals 2, S equal to 1, will give you a state which is symmetric under particle interchange. L equals 1, S equals 0. S equals 0 is spin antisymmetric. L equals 1 is odd under parity. So again you get a plus sign under particle interchange, something which is not possible. L equals 0, S equals 1 is ruled out. Again for a similar reason, here -1 to the L is +1 and S equals 1 once again is spin symmetric. So you cannot have L equals 0, S equals 1. This would have led to a symmetric wave function under particle interchange. The only possibility which remains is L equals 1, S equals 1. Here minus 1 to the L is minus 1 and S equals 1 is spin symmetric, and therefore the overall wave function is antisymmetric under particle interchange. So what we know at the end of this angular momentum conservation analysis, coupled with the fact that the final state particles are both fermions, is that the final state must be L equals 1, S equals 1. Now note that the initial state of this reaction was an L equal to 0 state, which is symmetric under the reversal of the individual momenta, whereas the final state is an L equals 1 state, which is actually antisymmetric under the reversal. So what we know is that if you were to calculate the S matrix element and then reverse all the three momenta involved, you must get an overall minus sign. The S matrix element must be odd. Notice that until now we have argued that if the product of the intrinsic parities differed between the initial and the final particles, then the S matrix element must be odd. We are actually using that argument in reverse now. Now that we know our initial state is L equal to 0 and final state is L equal to 1, from that we know that the S matrix element must be odd, and therefore the product of the initial intrinsic parities and the final intrinsic parities must differ. Eta pi minus times eta d must be equal to minus eta n square. Now, according to our convention, eta n is plus 1. And even if it had not been, the moment I'm using a p square, which is identity, all possible eigenvalues and therefore all possible intrinsic parity values must be either plus 1 or minus 1. Even in that case, minus eta n square would be minus 1. So, pi minus and the deuteron must have opposite intrinsic parities. Now, at this stage, it was already known that the deuteron is a Pn bound state with even L contributions only. This can also be figured out from symmetry principles. And most of the contribution actually came from the L equal to 0 state. So we know that eta deuteron is simply a product of the intrinsic parities of the neutron and the proton. In addition to this, or rather in multiplication to this, you should have an additional factor of minus 1 to the L, which is plus 1. And so eta for the deuteron is plus 1. And this immediately tells us that eta for the pi minus is minus 1. So using parity conservation and experimentally observed reactions, we managed to conclude that the pions are pseudo-scalar particles. Now this actually has far-reaching experimental consequences, and you can make rather important predictions based on them. One of these predictions is the following. A spinless particle that decays into 3 pions must have an intrinsic parity of minus 1. Here also, the argument is not as simple as it looks, because, well, you will see. Firstly, the argument goes this way. Since this must be a massive particle, after all it's decaying into 3 pions, it can be at rest in some frame. So in the rest frame of this particle, the S matrix element can depend only on the pion momenta. And there, rotational invariance will tell you that it cannot just depend on the pion momenta, I mean 3 momenta, in any way. It can only depend on the scalar products of these, because they are the only rotationally invariant objects. There is another rotationally invariant object here, which is P1 dot P2 cross P3. After we have three momenta for the 3 pions, and you could have possibly had this rotationally invariant scalar quantity as well. However, this must vanish because P1 plus P2 plus P3, the net 3 momenta of the outgoing pions, must be 0 from momentum conservation. Remember, the mother particle is in rest in the frame that we are talking about. Since P1 plus P2 plus P3 equals 0 means that the 3 vectors are in the same plane, the scalar triple product would vanish in this case. So the other possible candidate which S could depend upon is not allowed. S can only depend on the scalar product of the pairs of pion momenta. However, if that is the case, then reversing all the three momenta cannot change the S element simply because P1.P2, P1.P3 or P2.P3 are all invariant under the change all the P's go to minus P's. So the S element must be even, and therefore the total intrinsic parity, in this case the product of the intrinsic parities of the outgoing particles, must be equal to the intrinsic parity of the original particle. And therefore, you must conclude that the intrinsic parity of the initial particle, the one which decays into 3 pions, must have been minus 1. Similarly, a spinless particle that decays into 2 pions must have an intrinsic parity of plus 1. Exactly the same argument. And this leads to a huge observational problem. In the late 1940s, it was already known that there are two distinct particles, one which decays into 3 pions, another which decays into 2 pions. So, the first one was given an intrinsic parity of minus 1, the second one an intrinsic parity of plus 1, according to this calculation. However, these two particles were found to be identical in all other respects. So these two particles, the tau and the theta, were a great puzzle for elementary particle physics. We had two very different particles. You had two identical particles decaying in two different manners. And hence, being assigned two entirely different parities. Now, all kinds of mechanisms were thought of to figure out how this is possible. But then, two young physicists, Li and Yang, first made the rather bold proposal that parity reversal symmetry has not really been checked at the elementary particle physics level. And maybe the problem here is not explaining why these two different particles behave in such identical fashion. But the actual thing is, they are one and the same particle, decaying by two different modes, and they don't really have two different intrinsic parities. It's just that parity conservation, which we assumed in order to predict this, is what is at fault here. And this ultimately led to Madame Wu's famous experiment, which managed to overthrow the idea that parity is a symmetry for all possible interactions. Now, I'm not going to discuss this in great detail here for two reasons. One is this is a very lengthy subject and requires an entire set of videos on its own, perhaps. And another is that I have already made a semi-popular level video on this earlier in my Symmetries in Physics series. So if you are interested, you can take a look at that. I will give a link to this at the end of this video. So this is all I have to say about parity reversal symmetry and its consequence on S-matrix elements. In the next video, we are going to tackle the issue of time reversal symmetries and what consequences that has on scattering. Until then, bye.